topic is crystal structure optimization or relaxation. What is the goal of last year? I don't know why, but it was rather hard topic. But I personally I think that it has a really clear and very easy idea, very simple idea. Why do we use crystal structure optimization? Because the structures we take from some databases, they are not ideal, and because our calculation methods also not ideal. Because we don't have any DFT method which will correspond to experimental absolutely precisely. That's why all crystals that we take from some databases, they are not optimized for our system. What does it mean? It means that if we will apply, if we will provide some calculation, for example, I take some crystal from some database. It has some lattice structure. It has some atom coordinates. And I apply some pseudo functionals, for example, Perdue-Sunger functional, which we use for our calculations, and want to calculate the structure, calculate energy, or some other things. What will happen? When I start the calculation, I will notice that all the atoms has some forces acting on them, and that crystal structure is strained by some pressure. Why? Because it don't match with the result of the lowest energy from this calculation. Because if I will make some calculation with this structure, I can move atoms in some ways. I can change crystal. I can change crystal lattices, and I will get a slightly different structure with lower energy than I have in my input. So crystal structure optimization, why we call it also relaxation? Because we just decrease all the forces acting on the atoms to zero, and we decrease the pressure acting on crystal on lattice also to zero. So this is our goal. And structure with this released stress. So if we will remove all these forces, if we will remove this pressure, we'll get the lowest energy, and the structure will be will have the lowest energy. And I wrote this algorithm how to do it, and I just added to algorithm from our last laboratory work, this point, relaxation. So it can be combined with convergence test, and I recommend then use convergence test plus relaxation to get optimal parameters. But today we will not make convergence test because it needs some time, and for today we have a lot of work. So what I propose to do now, I propose Alexei to share his screen, and we have to fill the gaps in the this file. Yeah, you can make it bigger. You see the gaps. Then I will explain you all these new things like TPRN4 and some other things. But for now, we just had to fill all these gaps. So I browse CLDM1 and so on. So how you will do it? You can unmute yourself. Everything is perfect, and you can proceed with the materials project.
Okay. Right. Yeah. We are looking for carbon,
yeah.
I think.
So graphite is the lowest energy configuration of carbon. So you had to find, you see, this energy above convex hull. For zero, it gives you should from zero, yes. For zero, it's some trigonal carbon, so it's huge unit cell. You need this MP88, 48 hexagonal. Yes. it's slightly less than 0.01. I think that it's almost 0%. We need this. Yes, hexagonal. Sometimes it works not so well. There is to explore.
Sometimes it doesn't.
But we don't need this. We don't need this picture. We need the information below this picture. Here, yes, crystal structure. And what thing we first should to notice? Hexagonal. So we should to feel eyebrow, and eyebrow connected to crystal system. So our crystal system is hexagonal, and you had to choose. You can open pw.x quantum expressor and check our eyebrow. How we can feel it. So it's manual, and here you should find eyebrow first, and you should choose your eyebrow. Like in Mortal Kombat, choose your fighter, choose your eyebrow. Wyckoff hexagon, yes, it's 4. And you see, what CLDMs do we need for hexagonal? Here, CLDM 3, this is C divided by A. CLDM 3. And by default, for each of these eyebrows, we need CLDM 1, so it's by default. CLDM 1 always equals to A legislator. And for some like 4, we need CLDM 3 and CLDM 4 and some other things. We need CLDMs. And you can feel all this data. Eyebrow. No, we need and CLDM 3 and CLDM 1. CLDM 3, CLDM 1.
And what is it?
Equals.
What does it equal to?
It equals to A, but we should type the number.
Our number is here.
Yeah, but it's in extremes, but we need in bars.
So
I can tell you.
So 2 times more.
Yeah, I can tell you 2.47 divided by 0. It's like 467. 467 bars. And CLDM 3, we also need the number. We should take.
So it should be 780 by 247.
Divided by 247. 780.
I can just
you're waiting that I will calculate it. Okay.
780 but
No, we should type only one number, and it will be 3.15. 3. So we should type here just a number, and its ratio. So it has no units. Okay, eyebrow 4. You forgot eyebrow 4.
Correct.
Mihail, do you follow us? Okay. Eyebrow 4. CLDM 1, 3. Number of atoms.
Number of atoms.
How many atoms
should
in
be,
unit cell?
To something like 12.
CLDM 4.
Number of atoms is 4. Number of
CLDM 3, yeah. 3.15. Is C divided by A.
4, and then
yeah, number of atoms 4.
One. Number of types is 1, I think.
Yeah, because it's only carbon.
And then cutoff energy.
Cutoff energy, I recommend to. We can find it. We should choose it from some convergence test. I recommend to take 50 Rydberg because it should be.
Cutoff energy.
You can find it in some internet. We should take it from convergence test, or we can take rather good convergence, rather good number for. So I recommend take 50 or 60.
Let's take 60. 60. And that must be
yeah, and you have finished system, and then what? No, please comment again. We don't finish. We didn't finish with this one. So you can go. Yeah, you see. We don't have positions, atomic positions. I left atomic positions blank. Here will be the here will be atom names and atoms coordinates. How to, and what I recommend how to find the atomic positions. You see this Wyckoff symbols. Slightly later I will explain what does it mean, Wyckoff, but you can go up. You can go up. You can take this the lowest where the picture should be, under yes, and you can for example, you can take Pascal, yes, Pascal, and you download the file with atom coordinates. Pascal is a file with atom coordinates. You can open it with some notebook. Yeah, not a book, and you see the coordinates.
This is convenient.
Yeah, it's very convenient, and so you can copy. You see it.
And what's the difference between C4 1.0 and C4 direct?
The format of this file is the next. So you the first line is just your comment. You can write anything here. Then is some scale factor. For example, you can type here 2, and we will work with unit cell multiplied by 2. Here are unit vectors. So you see 7.8. It means that it's C atom. It's C lattice, and here it's like 2.47, but in hexagonal shape. So this three columns are just coordinates of our vectors, of our lattice vector.
So we should just take this.
No. It's lattice. Then we type name of atoms, C, number of atoms. Then direct, it means that we use coordinates according to our lattice vectors. In the it's like crystal in quantum space, and you should take this. Yeah, it's coordinates of each atom. But then in quantum espresso file, you should change. You should move this C on the beginning of the.
So I should type it manually.
You should type it with just right click.
Huh?
Crystal. Just right click.
This is also convenient.
Yeah, it's also convenient. And you should remove the C and place them on the beginning of. Last year, I just showed on laboratory works prepared files, and then I noticed that students can't do all the things because they're really rather easy, but you have to be familiar with them. See,
should it be centered?
Yeah. Oh, okay. It's for beauty. You can make it chaotic, but it's good. And you see, and you have this blank. You see crystal, and then no. Between the coordinates and atomic positions, you should delete this blank line. Yeah, and now you can save it.
Should we make the slash?
No. You are in insert mode. Escape. Yeah. Okay. So you can close your. You can stop sharing the video. And now I propose you to start the calculation because it will take some time. It will take maybe 8 or maybe 10 minutes. and it will be finished till we will proceed. PWX, then as in PW. Yes, with relax, yes. And to create the same but out. The same file but out. So I have started it here. You see, begin to relax, and now I will explain you what is happening. Okay, but before how we can check if we made everything correct? We can check it with SIGPass. SIGPass. Calculate my structure. And what we see here? Here I see graphite. Here it is. So it's okay. All these hexagonal things. Then I see brilliant zone. We will need brilliant zone slightly later. We'll use all these letters. Here we see space group number 194. And if you will check, if you will check materials project, you will see that the same. You will see that it's exactly the space group of graphite. And this is the coordinates of each atom, but in not in direct coordinates, but in Cartesian coordinates. Here you see scaled or direct coordinates, and here you see this Cartesian coordinates. Cartesians in just coordinates. You take some point as 0. For example, you take this point as 0, and then you know that X lattice is 2.47 angstroms. The same is B lattice, and C lattice is 7.8 angstroms. And you can take that. Okay, we use 0.25 from C from 7.8. You can divide 7.8 by 4, and you will get this thing in angstroms. And but we don't need. Usually we don't need them. And you see this suggested path. We also don't need. Now we use it just to check if everything okay. And I see that everything is okay. And I also want to show you another thing, how to deal with coordinates. What means this Wyckoff positions? Wyckoff positions. Yeah, it works rather bad. I think it's very heavy side, and a lot of people use it maybe more than these guys thought. Okay, what we have here, you see Wyckoff positions, atomic positions. The easiest way is just to export this. You take this, you take postcard, and then you see all atom coordinates. But also we see this thing. It's Wyckoff positions is some economic way to write these positions, because sometimes here we have 4 atoms, and it's not a big deal to type 4 atom coordinates. But sometimes we have 20 atoms, or 30, or 100, or 1,000 atoms. And in this case, it's Wyckoff positions are very useful, because for each position, we can type 20 atoms or 16 atoms or something. For example, here we have only 2 Wyckoff positions. Each stands for 2 atoms, 2b and 2c. Here the number is number 2. It means that it stands for 2 atoms. B and C means some symmetry operations. We will proceed with this operation. So we just made this short notice, and I will show you how to deal with it. You can open site Bilbao Crystallographic Server. Bilbao Crystallographic Server. It's a very useful site. Forthcoming some workshop in Australia. You can go in the site to space group symmetry. And in space group symmetry, you see this tag Wyckoff sets, equivalent sets of Wyckoff positions. And I go here. I should type here space group. What space group I have? I have 194 space group. I type it here. Then I show, and I see all Wyckoff positions for this space group. So our graphite is hexagonal structure with hexagonal space group, and we have all these symmetries. So inside this space group, we can fill these positions. They are called Wyckoff sets. Usually in non-amorphous materials. In amorphous materials, atoms can be everywhere, but in non-amorphous materials, atoms can fill only these positions. That's beauty of this mathematics. So it went from pure mathematics, from some groups, for some group mathematics, and in nature, in reality, atoms can be placed only in these positions in non-amorphous materials if we deal with some crystal structure. And you see space symmetry minus 6m2. What does it mean? 6, it means how many times we can rotate our structure. Maybe I can write it. I can draw it. Yeah, I think it's, I don't know, but I think that it's our seminar. Okay, I can, for example, if we have some square, how many times we can, rotate it with for the square goes looks the same. So if we will 4 times, yes, if we will move it here, and we have 4 times. 4 times. If we have some hexagonal, I'll try to, yes, I'll try to, yeah, we have 6 rotations, 6. And each rotation, on what angle we will have this rotation? 60 degrees, yes. And what does it mean this 6? It means that we should make 6 rotations. It means that we can make 6 rotations to this atom, go to the same position. What letters? A, B, C? It's just name of some symmetry operations. For example, A always stands for 0. A always stands for 0. B for this space group. Yes, we have space group 194, and we have all these symmetry operations. So we don't have any other symmetry operations for this group. And what is Wyckoff sets? It's when we apply some symmetry operation and we have the same structure. That's the idea. So we apply the symmetry operation and we get the same structure as we can rotate this hexagonal 6 times, and we will get this structure. That's why here we see 6. here I see mirror, because if I will mirror according to some central axis, I can mirror this thing, this, and I can mirror like this, and I will get the same structure. With some error. Okay, let's. So for this B position, if I have an atom in some B position, I can rotate it 6 times, and it will go to the same position. And I can mirror too. So I can make this mirror symmetry twice. So for this and for this. And now, what is interesting? We can make more detail. We can take all these symmetry operations, and we can take the coordinates of equivalent position. For example, for 2B, you remember in materials project, it was 2B 001 force. Yeah. Here you see that for 2B, we have 2 atoms. We have 2 coordinates. So 001 force and 003 force. Yes, it's mirror atom. So we have 2 mirror. So in this by this formula 001 and 2B, we stand for two atoms, 2 mirror atoms, and we can apply these symmetry operations on first atom on 001 force, and we will get another atom, or we will get the same atom. Then what else we have? We have 2C, 1/3, 2/3, 1/4, and it also means that it stands for 2 atoms. And what symmetry operations we have? We have the same symmetry operations. What means if we will rotate some coordinate 1/3? It will go to -1/3. Yeah. If I will take some coordinate 1/3, for example, it will be somewhere here. We can rotate it. It will be somewhere here. So it will be -1/3. And what means -1/3? It means the same as 2/3. It means the same as 2/3. So if we rotate this coordinate, if we will rotate 1/3, we will get 2/3. And if we will rotate 2/3, we will get 1/3. It all goes from this 6 rotation, from rotation on 60 on angle 60 degrees, and the same things and as 1/4 and 3/4.
What's MM2?
It means that we can mirror and then mirror. This means that we can rotate it twice. So it's and this symmetry, it means that we don't have any specific symmetry. We have only these coordinates. So we have some other coordinates which will go to okay, when we will make full rotation, we will get the same. So it means this means low symmetry. This is low symmetry. This is also rather low symmetry, but this is high symmetry because we have we have some symmetry operations, and we can make, for example, these 2 atoms into 1 atom. So this is some harder way how to find these coordinates. We can do it very simply. We can just copy it from Pascal file. But if we are familiar with this Wyckoff sets, we can go to this file, this site Bilbao, and you can see, you can find all these coordinates and all items types. So we can use some theoretical way this Bilbao, and we have some practical way just to take this file with these coordinates. But theoretical way with this Wyckoff positions, it's good to better understand this symmetry operations, how it works. Okay. We finished with the symmetry operation with this beautiful pictures. And I think that we can now we can go to the file. Here is my file. We have something new. We have in this calculation tag we see relax. We had only SCF or bands. SCF was for self-consistent field calculations. Bands was for non-self-consistent field calculations to create some band structure. But here we have these two new tags. Relax. It means that we allow atom positions to change. We can move atoms. And we see relax. It means that we can change atom positions and geometrical size of our unit cell. Then you will see from output how it changed. It changed a lot. We have two options. For this, we see relax. It means variable cell. Variable cell, like we can change geometrical shape of the unit cell, geometrical size, not shape, not shape. And this is full relaxation of the structure. Prefix pseudo you know, and what is it? TP4. These two tags, TP-RN4, I even can't read it. So 4 stands for forces, and stress means for stress, which applied to our unit cell. And we can find it in your output file. Then we will look at this output file. You can find the forces and you can find the stress. Forces will be in the same way. We will it takes the forces in some coordinates. It shows some force in each direction, x, y, z direction. For graphite, we have 0 forces which acting on the atoms because it has rather ideal coordinates. But we have rather huge stress. You see kilobars. You see this total stress on the cell. Each here vector for first unit, for first lattice vector, for the second and for the third lattice vector. So here we see how the stress acts on each coordinate of our unit cell vectors. And then it's in Rydberg divided by Bohr in the power of third. And here in kilobars, equivalent in kilobars, 63 kilobars. It's rather huge. So our structure was stressed. Our structure was hugely stressed with 63 kilobars when we took it from materials project. And then, so these two tags, they just allow this information to be in output. True, it means by default it's false. I just typed it true. And here a tot, it means total energy convergence threshold and forces convergence threshold. What means total energy convergence threshold? So it's not like this convergence threshold. This threshold in electrons, it deals only with the Kohn-Sham cycle. It's only for convergence of each Kohn-Sham cycle. But total energy, it means for each convergence for each ion step. For example, we take some structure, then we changed atom positions and its size in some way, calculated this energy, and we see the difference between new structure energy and previous structure energy. And our algorithm works till this condition will be filled. Okay, and some energy between ion steps and forces accuracy. And also we have these two new blocks. This block stands for atoms moving, ions dynamics. So we choose algorithm how we can move atoms, and the same thing for cell. For cell, we also have the cell dynamics. It means by which algorithm we can change the sizes of vectors. Cell do free. It means what parameters of shape we can change. If I take eyebrow, I tell the program that we should save the same symmetry, because I can, for example, okay, I will show you this in Quantum Espresso. pw.x. We have this ions block. Where is it? Here. Ions positions, ion dynamics. For example, ion dynamics. No, not ion dynamics. I was wrong. Cell do free, so it's for cell. I can select different models. For example, I can allow all axes and angles to change, and it's the hardest way of relaxation. So if I think that my structure is rather creepy, I can allow axes and angles moved, and I can go, if I'm lucky, I can go to better structure. I can use eyebrow, and eyebrow means that I also allow angles but axes moved, but they are moving in eyebrow if choosing eyebrow symmetry. If I have hexagonal symmetry, eyebrow 4, they will be moving to satisfy hexagonal symmetry conditions. I can also say that I want A, B, or C vector to be changed, or some specific coordinates to be changed, and so on. We will usually use eyebrow, and for two-dimensional crystals, we will work with them next time. We will use this 2D XY, because it will not work with eyebrow. And here is stress. Stress. I mean that stress acting on unit cell should be 0 or near 0, and press convergence threshold is the same thing. It should be 0. And what means BFGS? BFGS is some algorithm to relaxate. It was named for this 4 guys, mathematicians, Broyden, Fletcher, Goldfarb, Shano. Is very popular algorithm, and I will explain it. I'll try to explain it shortly. It's quasi-Newton algorithm. It works in the same way. I also will drive. I can drive it here. For example, we have some energy. We have some energy landscape. So each point of this line stands for some crystal structure, and we are looking for this structure because it will be the we are looking for this because here we have the lowest energy. But for example, we have started with this energy. We started with this energy. Then this algorithm changes atoms and cell shape, atoms positions and cell shape in the way to lower the energy. For example, it was succeed, and we got here. So we jumped from here to here. We jumped from here to here, and we had lower energy. And algorithm checked, okay, this move was correct. All previous moves, which, for example, got us here or here, it was not correct because energy was higher. But in this move, energy is lower. That's why this specific atomic positions changes or cell lattice changes was okay. And then it changes in the same way. For example, there was 4 atoms, and it moved 1 atom here, and all energy lowered, and then it moves other energy. Then it moves other atoms in rather same way to achieve lower energy, and it goes, for example, here. So it achieves lower energy, and so on till we get till we will get the lowest energy, or the lowest energy according to some stopping criteria, some stopping conditions. That's the main idea of this quasi-Newton methods. I hope you got it. And about mathematics, so we have we have some function, for example, function in next coordinate, in next step will be lower than in previous step. So this is energy function. Then we make some mathematics. So we have this Taylor expansion. Then we calculate some difference. So how it changed. So we can calculate some derivative. So how it was changed with this small delta x moving. So here is some derivative, and we work with our coordinates, because each coordinate is some set of just some set of numbers. So we can work with it. We can take derivative of this function. You see, derivative shows if our function goes up or our function goes down. So we use this derivative of this function. It's some numerical derivative which makes the algorithm. And then we can create some delta x. We can create some delta x step. So each time this step will be different. Will differ from previous time, because if this energy is converged, so this step will be not the same as this step. So we should scale our delta x to achieve convergence. In this mathematical way, we get some xn plus 1. So how we should change our x coordinate to fulfill the condition that this function value should be lower than previous value, and we should do in this way, where n is some Hermitian matrix. And how it realized in some programs as quantum expression. So this is some box schema, how to deal with it, and this is the same energy landscape, but from the top. So here is this energy landscape I wrote from the side, and here is this energy landscape from the top. We was here in x0, then we moved to x1, to x2, to 3, 4, and we got the lowest energy. And our atoms moving according to this algorithm, and our shell also, our cell also changes according to the algorithm. Rather simple algorithm. Okay, so let's proceed to some calculation results. What have we got? I think that all of you get this file, graphite VC relax out, and now we can work with it. results actually almost the same as results as output file for SCF calculation, but it's like we made a huge number of SCF calculations one by one, and all outputs we combined into the file. We have this information about key points, about the structure. So we have we saw it before. I want to maybe I want to move. Okay. Okay, it's information about some first calculation and what is new. So we saw all these things: key points, energy bands, this output, Fermi energy, total energy. But what's new? What new we have? We have this thing. I showed you this in the presentation. We have information about forces. 9 current error. Okay. If job is done, job is done. Something new we have forces acting atoms. For graphite has rather ideal structure, so atoms are located in this Wyckoff sets in some ideal positions. That's why it has no forces acting on atoms. If it had, so it would be decreased by the steps, but it had rather huge stress on the cell. You see that on first vector A, it like minus 63 kilobars, and on vector C, it's like minus 16 kilobars. So we had to remove the stress. And then we have some information about our algorithm. BFGS, this algorithm, geometry optimization. Energy error, because it's some first step, 0. We have nothing to compare with. Gradient error. Gradient error, it means forces or gradients. Almost 0, so we can neglect it. And cell gradient error. What does it mean? Cell gradient error is stress. The stress, and it shows that we have stress like 4.3 multiplied by 10 in the power of minus 4. Yeah. Then we have had number of SCF cycles 1, because we just made some SCF calculation, and number of BFGS steps 0, because we hadn't changed anything yet. And now we are doing these changes. You see, we change CLDM1 and CLDM3. So we just here we just finished some SCF calculations, some first SCF calculation to get forces, to get lattice stress, and then BFGS cycle begins. BFGS step. We change CLDM1 and CLDM3. It was, if you remember, it was something like 4.67, and it was like 3.15, but we changed it slightly, and input lattice vectors also was changed, and we make another calculation. So we make another calculation with these new parameters. Lattice parameters and atomic positions, but atomic positions wasn't changed because we deal only with cell. Yeah, maybe Mikhail, maybe you mean this thing. Yes, C bands agent value not converged. We changed atomic parameters of the cell, and then we begin new SCF cycle. We begin this just brand new SCF cycle, but with these parameters. We go, and we have some results. You see, total energy minus 71, 27, 4, 8. Let's check. In the previous step, minus 71, 27, 4, 5. It was 8. So total energy slightly decreased from this step. Then we also compute these forces. So forces are 0. It's not interesting, but stress was changed. It was like minus 63 kilobars, but now it's 57 kilobars. So it's changed on more than 100 kilobars in another. So it was like strain, but now it's like pressure. And we got, so we have made 2 SCF cycles, and we have made 1 BFGS steps. We didn't get the convergence. Why? Enthalpy old, you see, old energy was this, and new energy is this. So energy slightly decreased, 48, 40, 45. So energy is slightly decreased. That means that we are moving in the right position, in right direction. We made 2 SCF cycles, 1 BFGS step, and it's time for another BFGS step. That means that we change sodium-1 and sodium-3 again, slightly change them, change these lattice vectors, make new SCF cycle, get another information about kilobars. You see, it was like 57, now it's like 0.86. So it decreased this pressure effectively. This left, but this was decreased. This pressure was decreased on the second step. We have new energy. It was on the previous step. It was like 48. Now it's like 54. So energy also decreased slightly. That means that we are doing all correctly. Then we go on third BFGS step. We change sodium-1 and 3, and so on. Have new this SCF cycle, have new stress, and have new coordinates. And that's still the convergence. You see, this file is rather huge. We have rather big number of these things. 15 minutes. But 15 minutes is because my computer heavily works. Mikhail has 4 minutes. How much time do you have? 8 minutes. Yeah, maybe Mikhail's calculations was rather wrong, but I will check it. Then, okay, you see. And the last point, this is the last calculation. We see the stress, minus 0.2. We have started from 40 something. Here, 0.13, it was like minus 63 kilobars. So it's almost nothing. Here was minus 16, minus 0.87. So with this stress is was decreased successfully, and a program thinks that the stress is okay. So we can stop our calculation because we achieved this our calculation. Almost 0, minus 0.2. It was you also have the same, yeah? It's even better. We have final energy. This is final energy, 85. You remember that we started from 48, so we decreased the energy, we released the stress, and we got correct Fermi energy. First approach of Fermi energy was like 5 something electron volts. Now it's like 7 something electron volts. Okay, and we are going. We made relax. We made this first step of our calculations. Usually, it's much more faster because I explained you all the steps. And now we are going to what was the goal of this calculation? Our goal was what information we should get to some further calculations. We should get cell DM, we should get the shape cell DM1 and cell DM3, new cell DM1 and cell DM3, and we should get new atomic positions if they was changed. And I go to SCF folder. SCF folder, this graphite, it is also it's also have some blank sides, but we can fill it together very easily. Cell DM1, cell DM3, I don't fill yet. Cell DM3. An atom for type 1, 50, atomic coordinates. And I have new cell DM1 and cell DM3. Folder SCF, yeah, just common graphite SCF in file. And I should take cell DM1 and 3 from output from relaxation file. I also open this output. Here it is. I open this output and I go to some phrase with which final coordinates. Here's begin final coordinates. It's before last SCF cycle. So it means that we get new structure with these parameters, and then we make yet another SCF cycle just to get some energy. So new energy was like minus 71, 27, 90. You see some information, 2.34 gram per volume. It's like density, and you should get some new eyebrow and CDM here. So begin final coordinates, and slightly above final coordinates, you can get CDM 1 and 3 for the last structure, this, and just copy to and just copy them to SCF file. Copy paste. You see, it changed a lot. It was like for SLDM1, it was 4.67, so it's this change is not so huge. But SLDM3 changed a lot. It was 315. Now we have 268. That's the usual problem. And atomic positions we can just copy, for example, from here. New atomic positions. They are the same as atomic positions in relaxation, but it's the only reason they are the same is because we haven't any forces. If we have some forces acting on atoms, it means that atoms located in non-optimal positions, they will change. Here they haven't changed. Minds. And what else we have? We have N, B, and D. How do you think? How much we should type here? Number of bands. I want to calculate band structure of graphite. How do you think? How much we have? We have 4 carbon atoms. Each carbon atom has 4 valence electrons. 16, yeah. We can make it higher, but 16 is okay. So because if we will take, because by default it will be 8. By default, it thinks that all electrons sits by 2 electrons on one energy line, and that only valence band is filled. And here we say it to calculate conductive band also. So we got then we can copy it to so we can proceed by this algorithm. The algorithm is very is the same as for band structure creation. We made this relaxation step. We have found the most relevant atomic cell, unit cell. Then we use this unit cell to self-consistent calculation. Then we make some band structure calculation as we made it in last time, and then we just make post-processing. Now we should copy all files, all output files from self-consistent calculation folder to band structure folder, and it's I just copy it to bands. No, we should do something with this file. It was filled, yeah. So it was not empty, this file. Bands in, yeah. You should type here, because I took it from my test calculations. You should change the CLDM1 and C3 as the same as it was in the SCF. I think it should be. I think they should be almost the same. Yeah, they are almost the same. From SCF, yeah. Yeah, what I wanted to tell about brilliant zone. You see, yeah, bands dot x. We have this file bands dot in. I open it, and here I see these key points, crystal band. So it's some path in this hexagonal lattice. We have eight dots. So in silicon we had 5 dots. Here we have 8 dots. And how I choose it? I choose it with SIG path. We have this brilliant zone. You see, it's also hexagonal. It's hexagonal, and SIG path suggests me this path. So gamma m как gamma, a l h a. What they look like? Gamma first chain is gamma m. So here is gamma. Gamma is always center gamma. Then we go to m. M is the center of this plane. M is the center of this plane. Gamma m. Then we go to k. K is the center of this side line. K and gamma. So we have this triangle. Gamma m, k, gamma triangle. Then we have a, l, h, a. What does it mean? A, it's our border of brilliant zone. It's right up the gamma. So from gamma we move to a, and we have the same triangle. A, L right up on the M, the center of this side. M, H is the corner A. So we have one triangle. Then we move to the border of brilliant zone. And have another closed triangle. This is typical path of hexagonal lattice. So it's a typical path for every structure with the same space group as graphite, graphene, or some other things, so dihydrogenide, or some other things. And I can start it. Bands x, so pw dot x, graphite dot bands in dot bands out, and we should wait for a while. We should wait for a while. Everything works? Everything is fine. It happens. It's not a problem. If you see some messages that some eigenvalues are not convergent, it means that in some point of this quantum cycle, there was some small loops which wasn't convergent, so it's not a problem. It's a problem when all loops are not convergent. Да, може Zoom якась проблема. Okay, so then we. Oh, it still works. Went out. Okay, because my laptop is rather slow because of Zoom projector. Наступного разу вже буде темно, коли ми закінчувати наступного тижня. Все. It's finished. Then bands.x graphite. Yeah, graphite. Graphite band 2, yeah. Graphite band. Oh, now we are creating data for this plot, but I have already inserted it here in this plot. So the data. So Fermi energy, or maybe Fermi energy will be changed. I should check it. Fermi energy, I should find it. I can find it in graphite SCF in, SCF out. Graphite SCF out. Fermi energy. Then you should type it in. I have 7, 11, 27. It should be in our script. Fermi energy. And so in the script, I also made this high symmetry point coordinates. You just take it from this bands to out here this coordinates. So gamma, this is m, this is gamma, this is m, I don't remember, k, gamma, and so on. I place them here, and then I draw the lines and type these letters, and I can just Python 3.7 and then this graphite code guy. You also got this, yeah? I choose graphite because first because it changes rather a lot during relaxation, and because it has remarkable band plot, and it is remarkable because of these points. They call Dirac points or Dirac cones. You also got it, yeah? you see how beautiful they are. So here we see almost linear dispersion, energy dispersion, and in these points, electrons, they have very huge velocity, and this is one of that's one of reasons why graphene is so interesting material. So it's graphite, and why that was interesting to create graphene, because scientists have seen this band structure before in graphite, and they thought that, okay, this is really very interesting, this band structure, and if we can take not bulk material, but if we can just 2D material like graphene, we can just have it's even more interesting, this thing, because this is center of brilliant zone, this is some border of brilliant zone, this part is central part, and this part is border part, and here we see all these things. I can slightly zoom it. You see it's more almost ideal. And what else is interesting here? Yeah, what about graphene structure? Graphene is layered material, and graphite is layered material, and between these layers we have, so all these layers, they are connected with van der Waals forces. They are so this is some kind of Coulomb forces, and DFT works with them not so good. That's why we saw this huge decrease in CLDM3, because we choose LDA, we choose very simple functional, Perlitz-Ungel LDA functional. Then it decreased, and it calculates this distance between graphite layers not ideally. So it calculates, it's rather bad, I should say, with error like 20 or 15%. To calculate it correctly, we should add some van der Waals corrections, but maybe we will do it on some other lectures. And for today for today, that's all. Maybe you have some questions. Okay, so it's all.